as we said as we went over the homework, H2CO3 does some special stuff. Okay? H2CO3 is carbonic acid. Okay? And we've talked about carbonic acid a couple times already this chapter. Okay? Because what we did with carbonic acid is we wrote the decomposition. The carbonic acid decomposed into H2O and CO2. And we said, this is where the bubbles from your soda come from. Right? So if that's where the bubbles from your soda come from, that's a gas. So if this is the product of the double replacement reaction, it's not done reacting yet. It's going to fall apart one more time. You're going to make that in a double replacement, and then that thing that you made is going to fall apart. And you're going to get bubbles. And this is where we get the bubbles that leave the stuff. Is it gas that leaves? Because on the homework last night, there wasn't any that had the gas that leaves. We had mix the water, but we never had make a gas that leaves. This is where you're going to see the bubbles. I wrote the wrong thing. I'll fix that here in a second. Okay, so for example, if I put together sodium, come on, let me write in that spot. I don't know what it is. Sodium hydrogen carbonate and acetic acid. Everybody see sodium hydrogen carbonate and acetic acid? No, I didn't. No, it's C2H3O2. That's acetate. Put it. Oh, hydrogen carbonate, NaHCO3, sodium hydrogen carbonate. It's not carbonic acid. It's sodium hydrogen carbonate. Okay, recognize this is a double replacement reaction. Okay. Everybody see it's double replacement? Ionic and ionic. So sodium and H are going to change place. So the sodium will end up next to acetate, and the H will end up next to HCO3, which makes H2CO3. That make sense? So I'm going to have to rewrite it because there's really not room here. HCO3 plus HC2H3O2. So I'm going to make the sodium acetate, but that H2CO3 is going to fall apart into sodium acetate. That is sodium acetate. But my H2CO3 is going to fall apart into H2O and CO2. You have all seen this reaction. You've all done it. Because sodium hydrogen carbonate is baking soda. Acetic acid is vinegar. Poured together vinegar and baking soda in your science classes before? What happens if you pour together the vinegar and you make a whole bunch of bubbles? Those bubbles are the CO2. We'll talk about that later. It's actually one of the things that comes up. Okay. It's just decomposition of hydrogen peroxide catalyzed, yeah.
Just put two arrows now?
Oh no, so that means the CO2 would go up. H2O wouldn't fall down. This is aqueous. Sodium acetate, because it's got sodium, it's going to stay in solution. H2O is a liquid, so it doesn't fall to the bottom. So you can't use an arrow for it.
Two reaction arrows.
No, just actually we just I would do this and then put an arrow after it.
Okay.
A second arrow. Like I make this and then I make this. So it's going to happen every time you make H2CO3, it's going to fall apart and make bubbles on you. Just like every time you push the lever on the fountain at Legends, the bubbles come out of the water. Because it's the same thing. So if you make H2CO3, that H2CO3 falls apart and makes CO2, and that's how you get the gas that leaves, which makes double replacement reactions happen. You gotta have something that gets it out of ions in solution. So making it a solid, you don't have ions in solution. Make water, you don't have ions. You got rid of the H plus and the OH minus. Or if you make this gas, that CO2 leaves, and I don't have the carbonate ion anymore. So I lose ions when I do this. So that's what the double replacement reaction is. The driving force is, am I going to make something that separates from my solution? Okay, in some way, gets those ions out. So, as you found the other night, your first step is to recognize which type of reaction it is. So here's the ones I expect you to be able to recognize. Okay? And you're going to have to be able to recognize them from just the reactants. Because if I tell you what the products are, you're not trying to figure out what type it is. You're not trying to predict what it's going to make, which is the goal of doing types of reactions, is so you can predict it. Okay, I'm going to use a complicated system here. E is going to stand for element. Okay. C is going to stand for compound. So E for element, C for compound. So if my reactants are two elements, element plus element, that means separate pieces. Well, if I got separate pieces, the only way they can change is to come together and make one piece. So if I got separate pieces, the way they change is make one piece. So if you have two elements, the only way they can change is to come together and make a compound. If your reactants are just one compound, the only way one compound can change is by falling apart. Can't add anything else because there's nothing else to add to. So the way it can change is by coming into smaller pieces. If you have one element, one compound, that's single replacement. And if you have two compounds, and it's double replacement. So if you're expected to predict what it's going to make, these are the things I expect you to predict. If it's otherwise, if it's two compounds and it's combination, I will say this is combination. Does that make sense? But these are the ones I expect you to be able to predict. So, let's see if we can do this. What type of reaction is this? Well, H2 is an element. O2 is an element. If I have two elements, the only way they can change is to combine. And so we make that decision about what type it is. Then we do what the name says. The name says combine them, H and O. I don't bring the subscripts over. Then I use charges. O is 2 minus, H is 1 plus. H2O. Then balance. 2 H's, 2 H's, 2 O's, 1 O, so I got to put a 2 in front of H2O, which gives me 4 H's, so I got to put a 2 in front of H2. That's the process. Do what the name says. Figure out the formulas on the product side. Then balance. The only time you copy pieces from one side to the other is if polyatomic ions stay together. That's the only time you copy subscripts. Zn plus H2SO4. That's an element. That's a compound. That makes it single replacement. So I do that. The zinc would single replace. So the zinc will replace the hydrogen, ends up next to sulfate. Hydrogen will be off by itself. Can hydrogen be by itself? We've all been through that process a few times, right? Mercury 1 oxide. See, mercury 1 oxide. Okay. It's only got one compound, so it's got to be decomposition. I haven't used D yet. Doesn't it have to be D because I've done all the other ones? No. That's a compound. That's an element. Single replacement. Cl is going to replace. No, Cl is not going to replace K. Cl is going to try to replace Br. Can Cl replace Br? Cl is above Br on the table, so it can. So this reaction would happen. Right? So it doesn't matter which order they're written in, right? Because the plus sign is just the word and. So, because on Friday you got hugs and kisses, kisses and hugs, the same thing. Okay, and that would be, that's a double replacement, right? All right, so that's pretty easy to do because you got to make that decision because on the homework there's sections where they're mixed together. You have to decide what type it is before you can complete. All it says is, here's the reactants, complete and balanced. You got to figure out which type it is. Okay? And then we got one last type that doesn't match up with our dancing analogy at all. Okay? The last type is called combustion. So, when you think combustion, what do you think? Combustion. What word comes to mind when you think combustion? Fire, right? Fire. So, we got our fire triangle. What does it take to have a fire? Oxygen, fuel, heat. You got to have all three of those pieces. If you remove one of them, the fire goes out. Well, the fire provides its own heat most of the time, unless you throw water on it. The way water puts out a fire is it uses its energy to boil the water so it doesn't get hot. So it gets rid of the heat on your fire triangle. Because all the energy is going in to boil the water, not into making new flames. First, it's a couple of things. First, you're going to boil that water, so it's going to be a cloud of steam that's going to hit cold air and condense back out. You're also going to hit a whole bunch of ashes, and those ashes are really fine, so it'll kick up the dust in that cloud of steam. To me, that was what would cause it. Is you're seeing a cloud of fog, and the fog forms easily over the little pieces of ash. You need a seed to make those droplets show up. So that's why you get the big cloud of steam. It's mostly steam with a little bit of ash in it. Okay. So that's got heat. We'll talk about the energy part of it later. Right now, we're just worried about the other two legs, fuel and oxygen. Okay? So you're going to have a fuel, some compound, reacted with oxygen. What we notice is the heat and the light. The heat and the light are not matter. The heat and the light are energy. We haven't talked about energy in chemical reactions yet, but we will. And we are going to talk about combustion of a very narrow range of elements, the compounds. We're going to expect you to be able to do the combustion of compounds that have carbon and hydrogen. They have to have carbon and hydrogen. It's okay if they have oxygen, it's okay if they don't. So CH, C something, H something, O something, or just C something, H something. Okay, so right now my equation looks like C something, H something, O, maybe, plus oxygen makes. And what does it make? Well, the beauty is you don't have to figure out what it makes. It's a very limited set of products. It makes carbon dioxide and water. That's what it makes, carbon dioxide and water. That's called complete combustion. Now, Got a question for you. Who has ever seen water coming out of fire? That's what this says. But isn't that what that says? If I burn it, I'm going to make water. Okay? Maybe you have seen it. Okay, well, if it's gas, you're not going to see it, but anybody ever made mac and cheese on a gas stove? When you put the container of cold water on the stove and then light the fire, the outside of the pan gets wet. That's the water from the flames cooling off and condensing on the outside of the cold pot. So to show you it's not just a bunch of words on paper, because we hate just words on paper, I'll try to show it to you. So, change that hose for sure. So there's my fire. Can everybody see the water coming out of it? No, but here's how you see it. Put on that cold glass. When it hits the cold glass, you see the fog? That's the water coming out of the fire. You can't do it too long because it gets too hot and then it won't condense. And I burn my fingers. But get the idea? That there's gaseous water coming out here that we can't see. Okay? So the water comes out all the time, and we get CO2 every time. And that's what's leading to global warming, because CO2 traps infrared heat on Earth. So since we've been burning plants that died millions of years ago, every time we burn something, we make CO2. The more CO2 we get in the atmosphere, the more heat gets trapped. So anytime you're burning something, you're making CO2. Unless things aren't going well. It makes CO2 if things are going well. Sometimes things don't go well, and you don't make CO2. You only make carbon monoxide. That happens if there's not enough oxygen around. Somehow the oxygen supply gets cut back. It can't get enough oxygen to make CO2, so it makes CO. So that happens when the places like grills are not really efficient burners. Not designed to burn it most efficiently. It doesn't matter if you make carbon monoxide out in the backyard, but if you bring that grill into your house to heat it because your furnace went out, you're going to fill your house up with CO, and low concentrations of CO can kill you. Because what carbon monoxide does is it hangs on to oxygen, or it hangs on to hemoglobin better than oxygen does. So if you breathe it, it grabs onto that hemoglobin and doesn't let go, so the oxygen can't get into your body. Because when the hemoglobin gets to your lungs, it's already full and moves on. Okay? So that's how what it does is it suffocates you even though you're breathing plenty of oxygen, because the oxygen can't get in. So if, the other place it happens is things like you don't turn the heater on all summer, winter kicks on. During the summer, a bird built its nest in your exhaust. So the exhaust can't get out, so it backs up into your house. That's another way you can get carbon monoxide. That's why to sell or rent a house in California now, it has to come with a carbon monoxide detector. Okay, because it's silent, it's odorless, and all it does is make you tired, then you go to sleep. Okay. Sometimes it's really inefficient, and you don't even make CO. You just make C. We call that C soot. The black stuff coming off a candle, when you first light it, it's not burning efficiently. So you get that black soot, carbon and water. Okay with that? You've seen the soot come off before. The other pieces you've never seen, but you've seen the soot. Okay. Even if the compound has oxygen in it already, you still have to write plus O2. So there will always be two reactants, a fuel and oxygen. The fuel can have some oxygen in it, but it will always be a fuel and oxygen. So let me show you a demonstration. Here, write the formula for the complete combustion of this. Write the formula for this reaction. C4H10 is butane. Oh, we knew that. We did a lab on it. Oh. Okay, so I write my fuel, C4H10. That's one leg of my triangle. I also need oxygen. What's it going to make? CO2 plus H2O. It says complete combustion. Always make CO2 plus H2O. It's not a choice. It's always CO2 plus H2O. Then we go to balance this. So I got 4 carbons. I put a 4 in front of CO2. 10 hydrogens, so I put a 5 in front of H2O. That gives me 8 and 5, 13 oxygens on the right side, 2 on the left. Can I fix that? No, got even and odd, so I got to double the first one. And now I have 8 oxygens, change that to an 8. I got 20 hydrogens, so I got to change the water to a 10. That gives me 16 and 10, 26 oxygen. And I can fix that by putting 13 in front of O2. Everybody okay with that? Really hard? And what if it was the incomplete combustion? Oh, actually, we'll do both. Because I want to make a point about. So we'll do both types. That's why I left all this space. Both of them are going to have C4 plus H10, C4H10 plus O2, make. And I can, they're both going to make water, because we always make water. But one of them is going to make CO, the other is going to make just C. So there's the equations. Just have to balance them. I put a 4 in front of carbon monoxide, 5 in front of H2O. That gives me 9, which does me no good. So I put a 2 in front of C4H10. Make that an 8. Make that a 10. And that gives me 16, so that's 8. That's 18, it's 9, sorry. 18 is 9. I got to add 10 and 8 is 19, 18 last time I checked. Okay, and on the other one, 8 carbons and 10 waters. And I could put a 5 in front of O2. So according to the balanced equation, you can see that what makes the difference about whether this happens or not is how much oxygen you have. If you have lots of oxygen, 13, you make CO2. If you have less oxygen, you make CO. If you have even less oxygen, you just make C. 13, 9, and 5 molecules. Make sense? Write the formula for the complete combustion of C6H12O6. The first mistake people make with this is That's the fuel. You still have to write plus O2. So there's oxygen already, not enough to burn it. If you don't write that plus O2, it will never balance for you. So you make CO2 plus H2O. Now to balance. 6 carbons, 6 CO2s, 12 hydrogens, 6 H2Os. So on the right side, I've got 12 and 6, 18 oxygens. On the left-hand side, I got to get 18, but I've already got 6 taken care of. So I only need 12 more. So I put a 6 in front of O2. So don't forget that one when you're balancing. That's the other place people make mistakes. Is they see it there at the beginning and they want to not forget to write plus O2. The other one is they forget about that O when they go to balance because oxygen shows up in everything there. So I really want to leave it till the end. Anybody recognize this equation? Not from this year, but from last year. Last year you didn't call this combustion. You called it respiration. Cellular respiration. Glucose and oxygen makes carbon dioxide and water. You turn it around, water and carbon dioxide make glucose and oxygen. We call it photosynthesis. Okay? So this is where we get all our energy from. Okay? This is burning calories. Okay? So you burn calories to lose weight. Where's the weight go? Where does the weight go? When you lose weight, mass can't be created or destroyed. So where does the weight go? You breathe out CO2. That's where the weight goes. That's why exercise makes you breathe hard, because you need lots of oxygen so you can turn it into CO2. As you're breathing harder, you're exhaling more CO2, you're burning more calories. And so so if you weigh yourself at night before you go to bed and weigh yourself in the morning, you're going to weigh less. Every time, because you breathed all night. Just stop breathing at night, you won't weigh any less in the morning. I can't think of a way you could. Sleep eating, yeah. An IV, somebody put an IV in and gave you calories that way. Yeah. I don't know what those sensors would say. I don't know how those sensors would work. So, I've never been fed by a tube. So, and I try not to be. It's not something I'm looking forward to. Okay, so C2, H6O, and once again, plus O2. So if it just says incomplete, you get to pick either one. I'm going to pick the carbon monoxide. You choose between the two. So I would need 2 carbons, so I put 2 in front of carbon monoxide. 6 hydrogens, I put a 3 in front of water. That gives me 2 oxygens on the carbon monoxide and 3 in the water is a total of 5 oxygens on the right. And the left, oh, and I got that even thing. No, I don't. I got that one. So I want 5. I already got 1. I need 4 more. So it's got to be a 2. No, everybody okay with that?